Hi fellas, welcome to this video. With the release of GPT-4V and the launch of Adobe Firefly, it captures our imagination and makes us wonder what happens when machine can talk, can read, can see, can interact with us, just like human beings. The technology that enables that capability is called multimodality. Recently, I came across this blog post by Chip Huyen that talks about the landscape of multimodality and large language model. Today, I would like to go through this blog with my fellow machine learning practitioners and learn more about multimodality and its use cases. Before I start, I would like to introduce our reading assistant, Emma. She will help us go through this blog post, and I will inject my comments here and there during the course. So Emma, are you ready?
Yes, I'm ready. Thank you for the introduction. Let's get started. For a long time, each ML model operated in one data mode: text, translation, language modeling, image, object detection, image classification, or audio, speech recognition. However, natural intelligence is not limited to just a single modality. Humans can read and write text. We can see images and watch videos. We listen to music to relax and watch out for strange noises to detect danger. Being able to work with multimodal data is essential for us or any AI to operate in the real world. OpenAI noted in their GPT-4V system card that incorporating additional modalities, such as image inputs, into LLMs is viewed by some as a key frontier in AI research and development. Incorporating additional modalities to LLMs, large language models, creates LMMs, large multimodal models. In the last year, every week, a major research lab introduced a new LMM, e.g., DeepMind's Flamingo, Salesforce's Blip, Microsoft's Cosmos One, Google's PA-LME, and Tencent's Macaw LLM. Chatbots like ChatGPT and Gemini are LMMs. Not all multimodal systems are LMMs. For example, text-to-image models like Midjourney, Stable Diffusion, and DALL-E are multimodal but don't have a language model component. Multimodal can mean one or more of the following. Input and output are of different modalities, e.g., text-to-image, image-to-text. Inputs are multimodal, for example a system that can process both text and images. Outputs are multimodal, for example a system that can generate both text and images. 1. Understanding multimodal. Why multimodal? Many use cases are impossible without multimodality, especially those in industries that deal with a mixture of data modalities such as healthcare, robotics, e-commerce, retail, gaming, etc. An example of how multimodality can be used in healthcare. Image from multimodal biomedical AI. Not only that, incorporating data from other modalities can help boost model performance.
So let's pause here and quickly go over this image. So as we can see, a diagnosis can have multiple informations. It can have user and AI Q&As or user and doctor Q&As. It can have the doctor's or nurse's notes as described here. It can also have all kinds of imagery informations that's captured. So imagine we can combine all those together in one model and use that to help with diagnosis, to help with prescriptive analysis. How useful and how revolutionary that would be in the healthcare industry. So that's what this image is trying to illustrate. So let's get back to reading.
Performance. Shouldn't a model that can learn from both text and images perform better than a model that can learn from only text or only image? Multimodal systems can provide a more flexible interface, allowing you to interact with them in whichever way works best for you at the moment. Imagine you can ask a question by typing, talking, or just pointing your camera at something. One use case that I'm especially excited about is that multimodality can also enable visually impaired people to browse the internet and also navigate the real world. Some cool multimodal use cases from GPT-4V.
So in this image, there are some interesting examples. For example, here, describe the pointer region in the image. So here I'm assuming what's uploaded, it's a table in image format and it's able to capture a column. I'm assuming underneath there's some sort of OCR conversion what's really cool is when you can talk to AI in image, then there's something that you cannot convey with words, right? For example, how appetite are these apples? How do you even communicate that through image, right? This is also the other example of healthcare when you show which wisdom tooth is hardest to remove, right? It's really hard to describe, but the picture says a thousand words. So let's get back to the reading.
4 volts. Data modalities. Different data modes are text, image, audio, tabular data, etc. One data mode can be represented or approximated in another data mode. For example, audio can be represented as images. Speech can be transcribed into text, though its text-only representation loses information such as volume, intonation, pauses, etc. An image can be represented as a vector, which, in turn, can be flattened and represented as a sequence of text tokens. A video is a sequence of images plus audio. ML models today mostly treat videos as sequences of images. This is a severe limitation, as sounds have proved to be just as important as visuals for videos. 88% of TikTok users shared that sound is essential for their TikTok experience. A text can be represented as an image if you simply take a picture of it. A data table can be converted into a chart, which is an image. How about other data modalities? All digital data formats can be represented using bit strings, strings of 0 and 1, or byte strings. A model that can effectively learn from bit strings or byte strings will be very powerful, and it can learn from any data mode. There are other data modalities we haven't touched on, such as graphs and 3D assets. We also haven't touched on the formats used to represent smell and touch, haptics. In ML today, audio is still largely treated as a voice-based alternative to text. The most common use cases for audio are still speech recognition, speech-to-text, and speech synthesis, text-to-speech. Non-speech audio use cases, for example music generation, are still pretty niche. See the fake Drake and Weeknd song and music gen model on Hugging Face.
Wow, I gotta pause here. So I'm a fan of both artists. Let's see how real this one sounds.
Like Celine,
okay.
Bumping Justin Bieber,
it sounds like one of his songs.
And left, she know what she need, or her need, or she blessed, giving me my best, yeah. I got my heart on my sleeve with a knife in my back, what's with that, 20 in my world. Could keep sticking with Lambo for a drive, it's on the fancy door, and she buy out the store. I got my heart on my sleeve with the city, not a flex, what's with that,
Very interesting. So it's not exactly what I expect. It's more what you think AI would do, which is instead of creation, it just take pieces here and there from artist's existing song and kind of mix them together into this song. So it's a meh. Imagine AI can actually create, which I doubt. I think it's hard to have very nuanced inspiration. So this is another sign where I think AI would not replace true artists. I think AI can replace those artists that copy people here and there and just make small tweaks, but they cannot replace true artists that come up with their own style. So that's that. Let's resume.
Hugging Face. Image is perhaps the most versatile format for model inputs, as it can be used to represent text, tabular data, audio, and to some extent, videos. There's also so much more visual data than text data. We have phones/webcams that constantly take pictures and videos today. Text is a much more powerful mode for model outputs. A model that can generate images can only be used for image generation, whereas a model that can generate text can be used for many tasks: summarization, translation, reasoning, question answering, etc. For simplicity, we'll focus on two modalities, images and text. The learnings can be somewhat generalized to other modalities. Multimodal tasks. To understand multimodal systems, it's helpful to look at the tasks they are built to solve. There are many tasks and many possible ways to organize them. In literature, I commonly see vision language tasks divided into two groups: generation and vision language understanding, VLU, which is the umbrella term for all tasks that don't require generation. The line between these two groups is blurred, as being able to generate answers requires understanding too. Generation. For generative tasks, the output can be unimodal, for example text, image, 3D rendering, or multimodal. While unimodal outputs are common today, multimodal outputs are still shaping up. We'll discuss multimodal outputs at the end of this post. Image generation, text-to-image synthesis. This task category is straightforward. Examples: DALL-E, Stable Diffusion, and Midjourney. Text generation. A common text generation task is visual question answering. Instead of relying only on text for the context, you can give the model both text and images. Imagine you can point your camera to anything and ask questions like, "My car won't start. What's wrong with it? How to make this dish? Or what is this meme about?" Another common use case is image captioning, which can be used as part of a text-based image retrieval system. An organization might have millions, if not billions, of images, product images, graphs, designs, team pictures, promotional materials, etc. AI can automatically generate captions and metadata for them, making it easier to find the exact images you want. Vision language understanding. We'll zoom into two task types: classification and text-based image retrieval, TBIR. Classification. Classification models can only generate outputs that belong to a predetermined list of classes. This works when you only care about a fixed number of outcomes. For example, an OCR system only needs to predict if a visual is one of the known characters, for example a digit or a letter. Side note, an OCR system processes data at a character level. When used together with a system that can understand the broader context, it can improve use cases such as allowing you to talk to any textbook, contract, assembly instructions, etc. Document processing with GPT-4V. The model's mistake is highlighted in red. One related.
So here it basically mistakes the hair. It's not able to understand hair because it's not even in the list, I think.
Related task to classification is image-to-text retrieval. Given an image and a pool of predefined texts, find the text that's most likely to accompany the image. This can be helpful for product image search, i.e. retrieving product reviews from a picture. Text-based image retrieval, image search. Image search matters not only for search engines but also for enterprises to be able to search through all their internal images and documents. Some people call text-based image retrieval text-to-image retrieval. There are several approaches to text-based image retrieval. Two of them are: generate captions and metadata for each image, either manually or automatically. See image captioning in text generation. Given a text query, find images whose caption/metadata are closest to this text query. Train a joint embedding space for both images and text. Given a text query, generate an embedding for this query, and find all images whose embeddings are closest to this embedding. The second approach is more flexible, and I believe will be more widely used.
So the keyword here is will be more widely used, because the first one here, generating captions for image, are currently more widely used in enterprise setting where a lot of image upload requires people to put in metadata. I can see a world where people can take those images and generate additional metadata and use that join with the manual input text to generate a text embedding. I do see the second case has benefit if it's fine-tuned, but it can also be noisy. As far as I know, most of the cases nowadays when they process images, like even for the ones in YouTube, they rely heavily on the first one.
Used. This approach requires having a strong joint embedding space for both vision and language, like the one that OpenAI's Clip developed. Part 2. Fundamentals of multimodal training. Given the existence of so many amazing multimodal systems, a challenge of writing this post is choosing which systems to focus on. In the end, I decided to focus on two models, Clip, 2021, and Flamingo, 2022, both for their significance as well as availability and clarity of public details. Clip was the first model that could generalize to multiple image classification tasks with zero and few shot learning. Flamingo wasn't the first large multimodal model that could generate open-ended responses, Salesforce's Blip came out 3 months prior. However, Flamingo's strong performance prompted some to consider it the GPT-3 moment in the multimodal domain. Even though these two models are older, many techniques they use are still relevant today. I hope they serve as the foundation to understanding newer models. The multimodal space is evolving rapidly, with many new ideas being developed. We'll go over these newer models in Part 3. At a high level, a multimodal system consists of the following components: an encoder for each data modality to generate the embeddings for data of that modality, a way to align embeddings of different modalities into the same multimodal embedding space, generative models only, a language model to generate text responses. Since inputs can contain both text and visuals, new techniques need to be developed to allow the language model to condition its responses on not just text, but also visuals. Ideally, as many of these components should be pre-trained and reusable as possible. CLIP, Contrastive Language Image Pre-training. CLIP's key contribution is its ability to map data of different modalities, text and images, into a shared embedding space. This shared multimodal embedding space makes text-to-image and image-to-text tasks so much easier. Training this multimodal embedding space also produced a strong image encoder, which allows CLIP to achieve competitive zero-shot performance on many image classification tasks. This strong image encoder can be used for many other tasks: image generation, visual question answering, and text-based image retrieval. Flamingo and LLaVA use CLIP as their image encoder. DALL-E uses CLIP to re-rank generated images. It's unclear if GPT-4V uses CLIP. Zero-shot image classification with CLIP. CLIP leveraged natural language supervision and contrastive learning, which allowed CLIP to both scale up their data and make training more efficient. We'll go over why/how these two techniques work. CLIP's high-level architecture. CLIP's architecture. Both encoders and projection matrices are jointly trained together from scratch. The training goal is to maximize the similarity scores of the right, image, text, pairings while minimizing the similarity scores of the wrong pairings. Contrastive learning.
Now let's pause right here to take a look at this diagram. This is really cute. It has a little hamster with this rave glasses. So happy, hippie, hamster. So you have a text encoder and image encoder, and both encoder generates a vector of embeddings, and I'm assuming there is a function that projects the embedding into a matrix. This part is not very clear to me. Actually, it makes sense, right? Because it says DO times DI, so you are a DV, so DO times DV. So there is some sort of projection to say I cannot directly compare distance of these two text and image embedding because they're not in the same space. A easy way to do is just convert them, obviously through trainable weights, into a matrix like this purple one and this green one right here. And then from there, I'm assuming there's some sort of activation function to condense them into multimodal, or it's just text embeddings and image embeddings. So multimodal embeddings, these two embeddings, and then this is a very classic way, just cosine similarity score as the loss function. So on a high level, it just takes text embedding and image embedding, generate two embeddings, and project them into a different matrix. So basically, project from a vector to a matrix with a bunch of trainable weights, and try to condense those matrix into another embedding space. That way, the text and image can be on the same space. So that's the high level of what this diagram is trying to describe.
Learning. For the image encoder, the authors experimented with both ResNet and VEET. Their best performing model is VEET-L/14 at 336px. Large Vision Transformer, VEET-L. 14 patches, each image is divided into 14 sub-images. On 336 by 336 pixel input. For the text encoder, CLIP uses a transformer model similar to GPT-2 but smaller. Their base model has only 63 M parameters with 8 attention heads. The authors found CLIP's performance to be less sensitive to the capacity of the text encoder. Embeddings generated by the image encoder and text encoder are projected into the same embedding space using two projection matrices WV and WL. Given an image embedding by, the corresponding multimodal embedding is computed as WV. Given a text embedding Li, the corresponding multimodal embedding is computed as WL. When people say CLIP embeddings, they either refer to these multimodal embeddings or the embeddings generated by CLIP's image encoder. Natural language supervision. For many years, image models were trained with manually annotated image text datasets, e.g., ImageNet, MS Coco. This isn't scalable. Manual annotation is time-consuming and expensive. The CLIP paper noted that none of the then available image text datasets was big and high quality enough. They created their own dataset, 400M image text pairs, as follows. Construct a list of 500.
Wow, that is a lot. 400 million image and text pair. I'm wondering how much money they paid for the human eval annotators. But yeah, this is another one of those issues with the type of ML task like this where it doesn't have a clear predictable label like video clicks or ads clicks. A lot of it rely on human evaluators label, and that's what makes it very expensive.
500,000 queries. Queries are common words, bigrams, and titles of popular Wikipedia articles. Find images matching these queries, string and substring match. The paper mentioned this search did not happen on search engines but didn't specify where. My theory is that since OpenAI already scraped the entire internet for their GPT models, they probably just queried their internal database. Each image is paired with a text that co-occurs with it, for example captions, comments, instead of the query since queries are too short to be descriptive. Because some queries are more popular than others, to avoid data imbalance, they used at most 20K images for a query. Contrastive learning. Pre-CLIP, most vision language models were trained using a classifier or language model objectives. Contrastive objective is a clever technique that allows CLIP to scale and generalize to multiple tasks. We'll show why the contrastive objective works better for CLIP using an example task of image captioning. Given an image, generate a text that describes it. Classifier objective. A classifier predicts the correct class among a predetermined list of classes. This works when the output space is finite. Previous models that work with image, text, pair datasets all had this limitation. For example, models working with IL-CIRC 2012 limited themselves to 1,000 classes, and JFT 300M to 18,291 classes. This objective limits not only the model's capacity to output meaningful responses but also its capacity for zero-shot learning. Say, if the model was trained to predict among 10 classes, it won't work for a task that has 100 classes. Language model objective. If a classifier outputs only one class for each input, a language model outputs a sequence of classes. Each generated class is called a token. Each token is from a predetermined list, the vocabulary, of the language model. Classifier versus language model objectives. Contrastive objective. While the language model objective allows for vastly more flexible outputs, CLIP authors noted this objective made the training difficult. They hypothesized that this is because the model tries to generate exactly the text accompanying each image, while many possible texts can accompany an image, alt text, caption, comments, etc. For example, in the Flickr 30K dataset, each image has 5 captions provided by human annotators, and the captions for the same image can be very different. Contrastive learning is to overcome this challenge. Instead of predicting the exact text of each image, CLIP was trained to predict whether a text is more likely to accompany an image than other texts. For each batch of NN image text pairs, the model generates N text embeddings and N image embeddings. Let v1, v2, vn v1, v2, vn be the embeddings for the NN images. Let L1, L2, ln L1, L2, lane be the embeddings for the NN texts. Clip computes the cosine similarity scores of the N2 possible by LJ pairings. The model is trained to maximize the similarity scores of the NN correct pairings while minimizing the scores of the N2, NN2, and incorrect pairings. For clip, n equals 32,768, n equals 32,768. Another way to look at this is that each training batch of clip is 2 classification tasks. Each image can be paired with n possible texts, and the model tries to predict the correct one.
So a very interesting point is here is that it's not trying to predict the exact caption for an image, because that would be super hard. It's trying to predict how likely is a caption map to an image. So that is a simpler task that we can train the model to do. And I'm assuming by doing that, the model will learn the relationship between image and text and somehow able to produce a higher quality caption. So let's continue to read and see if that makes sense.
This is the same setup as image to text retrieval. Each text can be paired with n possible images, and the model tries to predict the correct image. This is the same setup as text to image retrieval. The sum of the
This formula looks pretty daunting, but it's essentially just a log loss, if I read it correctly.
These two losses is minimized. Beta is a trainable inverse temperature parameter. This is what it all looks like in pseudocode. Clip authors found that the contrastive objective provided a 12x improvement in efficiency compared to the language model objective baseline while producing higher quality image embeddings. Clip applications, classification. Today, for many image classification tasks, Clip is still a strong out-of-the-box baseline to be used as is or fine-tuned. Text-based image retrieval. Since Clip's training process was conceptually similar to image-to-text retrieval and text-to-image retrieval, Clip displays significant promise for widely applicable tasks like image retrieval or search. However, on image retrieval, Clip's performance relative to the overall state-of-the-art is noticeably lower. There are attempts to use Clip for image retrieval. For example, Clip retrieval package works as follows. Generate Clip embeddings for all your images and store them in a vector database. For each text query, generate a Clip embedding for this text. Query in the vector database for all images whose embeddings are close to this text query embedding. Image generation. Clip's joined image text embeddings are useful for image generation. Given a text prompt, DALL-E 2021 generates many different visuals and uses Clip to re-rank these visuals before showing the top visuals to users. In 2022, OpenAI introduced UnClip, a text-to-image synthesis model conditioned on Clip latents. It consists of two main components. Clip is trained and frozen. The pre-trained Clip model can generate embeddings for both text and images in the same embedding space. Two things happen at image generation. Use Clip to generate embedding for this text. Use a diffusion decoder to generate images conditioned on this embedding. Text generation, visual question answering, captioning. Clip authors did attempt to create a model for text.
Let's pause here and take a look at this figure. Here we have a text encoder that takes input of a corgi. So this looks like a diffusion model. Text input is a corgi playing a flame-throwing trumpet. Okay. So that text encoder generates an embedding, and that embedding goes to two different paths. So let's read this description. A high-level overview of an Huyen clip. Above the dotted line, we depict the clip training process, which we learn a joint representation space for text and image. Below the dotted line, we depict our text-to-image generation. So above the dotted line is a ranking model, I'm assuming, to generate text-to-image similarity. Below the dotted line, we depict our text-to-image generation process. A clip text embedding is first fed to an autoregressive or diffusion prior to producing an image embedding. And then this embedding is used as a condition condition a diffusion decoder which produces the final image. So they basically fine-tune clip, and then after that they use a diffusion model. Yeah, so as described here, use clip to generate embedding for this text. Use a diffusion encoder to generate image conditioned to this embedding. Know that the clip model is frozen during training of the prior encoder. It sounds like the high level is just using clips embedding to generate, use clips embedding, text embedding, somehow fit into a diffusion model to generate image.
Text generation. One version they experimented with is called LMRN50. Though this model could generate text responses, its performance was consistently around 10% below CLIP's best performing model on all the vision language understanding tasks that CLIP was evaluated on. While today CLIP isn't used directly for text generation, its image encoder is often the backbone for LMMs that can generate texts. Flamingo, the dawns of LMMs. Unlike CLIP, Flamingo can generate text responses. In a reductive view, Flamingo is CLIP plus a language model, with added techniques to make it possible for the language model to generate text tokens conditioned on both visual and text inputs. Flamingo can generate text responses conditioned on both text and images.
Let's see. So someone posted this dog and it's able to talk. That's conversation based on image and text. There's also conversation that has text and image in combined, and it's able to carry a discussion based on that. Interesting.
Images. Flamingo's high-level architecture. At a high level, Flamingo consists of two parts. Vision encoder. A clip-like model is trained using contrastive learning. The text encoder of this model is then discarded. The vision encoder is frozen to be used in the main model. Language model. Flamingo fine-tunes Chinchilla to generate text tokens, conditioned on visuals and text, using language model loss, with two additional components: perceiver resampler and gated satin dense layers. We'll discuss them later in this blog. Data. Flamingo used 4 datasets: 2 image, text, pair datasets, 1 video, text, pair dataset, and 1 interleaved image and text dataset. Dataset type size. How training weight. Interleaved image and text dataset 43 web pages for each web page. They sample a random subsequence of 256 tokens and take up to the first 5 images included in the sampled sequence. 1.0 align image, text, pairs 1.8b pairs texts are all texts, averaging 12 tokens /text.0. Tooltip image, text, pairs 312 pairs texts are long descriptions, averaging 20.5 tokens /text.0. 2 VTP video, text, pairs 27 short videos / 22 seconds /video on average 0.03. Flamingo's vision encoder. Flamingo first trains a clip-like model from scratch using contrastive learning. This component only uses the 2 image, text, pair datasets, align and tip, totaling 2.1 image, text, pairs. This is 5x larger than the dataset clip was trained on. For the text encoder, Flamingo uses BERT instead of GPT-2. For the vision encoder, Flamingo uses a normalizer-free ResNet, NFNet F6 model. Text and vision embeddings are mean-pooled before being projected to the joint embedding space. Flamingo's language model. Flamingo uses Chinchilla as their language model. More specifically, they freeze the 9 pre-trained Chinchilla LM layers. A traditional language model predicts the next text token based on the preceding text tokens. Flamingo predicts the next text token based on both the preceding text and visual tokens. Next token generation is conditioned on both text and visual tokens. Illustration taken from Chip Huyen Lee's CVPR 2023 tutorial, Large Multimodal Models. To be able to generate text conditioned on both text and visual inputs, Flamingo relied on perceiver resampler and gated satin dense layers. Perceiver resampler. As the visual inputs can be both images and videos, the vision encoder can produce a variable number of image or video features. Perceiver resampler converts these variable features into a consistent 64 visual outputs. Interestingly enough, while training the vision encoder, the resolution used was 288 by 288. However, at this phase, visual inputs are resized to 320 x 320. It's been shown that a higher test time resolution can lead to improved performance when using CNNs. Gated satin dense layers. Gated satin dense layers are inserted between existing and frozen LM layers to allow the language model to attend more efficiently to the visual tokens when generating text tokens. Without these layers, Flamingo authors noted a drop of 4.2% in the overall score. Loss function. Flamingo computes the likelihood of text conditioned on the interleaved images and videos X. The training loss function was a weighted sum of expected negative log likelihoods of generated text across all four datasets, with lambda m being the training weight of dataset M. Training. While the chinchilla LM layers are fine-tuned and frozen, the additional components are trained from scratch, using all four Flamingo datasets, with different weights. Finding the right per dataset weights was key to performance. The weight for each dataset is in the training weight column in the dataset table above. VTP's weight is much smaller than other datasets, 0.03 compared to 0.2 and 1, so its contribution to the training should be minimal. However, the authors noted that removing this dataset negatively affects performance on all video tasks. While Flamingo isn't open-sourced, there are many open-source replications of Flamingo. Part 3. Research directions for LMMs. CLIP is 3 years old and Flamingo is almost 2. While their architectures serve as a good foundation for us to understand how LMMs are built, there have been many new progresses in the space. Here are a few directions that I'm excited about. This is far from an exhaustive list, both because this post has been long and because I'm still learning about the space too. If you have any pointers or suggestions, please let me know. Incorporating more data modalities. Today, most multimodal systems work with text and images. It's only a matter of time before we need systems that can incorporate other modalities such as videos, music, and 3D. Wouldn't it be amazing to have one shared embedding space for all data modalities? Examples of works in this space. ULIP, learning a unified representation of language, images, and point clouds for 3D understanding, Shui et al., DEC 2022. Image bind, one embedding space to bind them all, Girdhar et al., May 2023. Jeff Dean's Ambitious Pathways Project, 2021. Its vision is to enable multimodal models that encompass vision, auditory, and language understanding simultaneously. Multimodal systems for instruction following. Flamingo was trained for completion, but not for dialogue or for following instructions. If you're not familiar with completion versus dialogue, check out my post on RLHF. Many people are working on building LMMs that can follow instructions and have conversations, such as multi-instruct, improving multimodal zero-shot learning via instruction tuning, Chu et al., DEC 2022. Java, visual instruction tuning, Liu et al., April 28, 2023. Instruct Blip, towards general-purpose vision language models with instruction tuning, Salesforce, May 11, 2023. LaVin, cheap and quick, efficient vision language instruction tuning for large language models, Luo et al., May 24, 2023. Examples of LaVin's outputs compared to other LMMs, shown in LaVin's paper. Adapters for more efficient multimodal training. While Flamingo used 9 pre-trained and frozen layers from Chinchilla, it had to pre-train its vision encoder, perceiver resampler, and gated satin dense layers from scratch. These train-from-scratch modules could be compute-intensive. Many works focus on more efficient ways to bootstrap multimodal systems using less training from scratch. Some works are quite promising. Blip 2, for example, Outperformed Flamingo ADB by 8.7% on zero-shot VQA-V2 with 54x fewer trainable parameters. Works in this space include BLIP2, bootstrapping language image pre-training with frozen image encoders and large language models. Lavin, cheap and quick, efficient vision language instruction tuning for large language models. Llama Adapter V2, parameter-efficient visual instruction model. The two images below are from Chip Huyen Lee's Large Multimodal Models tutorial at CVPR 2023, which is, BTW, an excellent tutorial. Generating multimodal outputs. While models that can process multimodal inputs are becoming the norm, multimodal output is still lagging. Many use cases require multimodal outputs. For example, if we ask ChatGPT to explain RLHF, an effective explanation might require graphs, equations, and even simple animations. To generate multimodal outputs, a model would first need to generate a shared intermediate output. One key question is what the intermediate output would look like. One option for intermediate output is text, which will then be used to generate/synthesize other actions. For example, CM3, Aghianian et al., 2022, outputs HTML markup which can be compiled into web pages that contain not only text but also formattings, links, and images. GPT-4V generates latex code, which can then be reconstructed as data tables. Sampled outputs from CM3. GPT-4V generates latex code, which can then be reconstructed as a data table. Another option for intermediate output would be multimodal tokens. This is the option that Kaiming Xiang, whose team at Salesforce has done a lot of awesome work on multimodality, told me. Each token will have a tag to denote whether it's a text token or an image token. Image tokens will then be input into an image model like Diffusion to generate images. Text tokens will then be input into a language model. Generating images with multimodal language models, Ko et al., June 2023, is an awesome paper that shows how LMMs can generate and retrieve images together with generating texts. See below. Conclusion. It's been a lot of fun going over so many multimodal papers as well as talking to people doing awesome work trying to summarize the key patterns in one blog post. There's so much about multimodality that I'm sure there are many things that I've missed, but I hope that this post provides the core patterns that will help you develop multimodal systems and apply them to your work. As you see in part 3 of this post, we're still in the early days of multimodal systems, so early that a friend told me he's not sure if the LMM abbreviation would catch on. Yes, in most of my conversations, there's little doubt that multimodal systems in general, and LMMs in particular, will be even more impactful than large language models. However, keep in mind that LMMs do not make LLMs obsolete. As LMMs extend upon LLMs, the performance of an LMM relies on the performance of its base LLM. Many labs that work on multimodal systems work on LLMs in parallel.
Alright, that's it for this blog post. For those who are confused about the abbreviation, LLM stands for Large Language Model and LMM stands for Large Multi-Modality Model. I personally find this blog very informative and made me very excited and want to read more about the multimodality, all the multimodality papers and some of the cutting edge improvements in this field. Let us know in the comment section which research direction of multimodality are you most excited about. For me personally, I am very excited about having multimodality output as generative model because a lot of answers, a lot of explanation, a lot of instructions will require more than just text format. That's it for this video. Thanks for watching. If you like this video, if you like this format, let us know. Leave a comment, hit the like button, subscribe. Thank you for your support.